Humanoid robots aren't science fiction anymore. They're showing up in labs, factories, and viral videos, moving through our world on two legs and learning to use our tools. Today we're putting three of the most talked about machines side by side: Tesla Optimus, Unitree G1, and Boston Dynamics Atlas. To see not just who can run fastest or jump highest, but what each one is actually for, how it sees the world, how it uses its hands, how it powers itself, and where it's most likely to work in the real world next. Think of it as three different answers to the same question. If you build a robot shaped like a person, what should it do first? Let's set the stage with purpose, because purpose drives design. Tesla's Optimus is the mass market bet. It's a general-purpose helper for boring, repetitive, and unsafe jobs, built with the same manufacturing mindset Tesla uses for cars. The long-term vision is scale. Millions of units doing useful tasks priced less than a car once it reaches volume. Atlas takes a very different path. Boston Dynamics built it as a peak performance platform for dynamic motion and manipulation in tough industrial settings. It showcases extreme mobility first and commercialization second, with early deployments planned with partners like Hyundai. Then there's Unitree's G1, engineered to be radically accessible. It's smaller, portable, and priced to invite a community of researchers, developers, and startups to experiment, extend, and build new behaviors on top. Three philosophies, three markets, three roadmaps. When we look at how these robots move, their differences become even clearer. Walking is simple for people. Walking on motors isn't as easy as it looks. Optimus isn't the fastest robot here, but it keeps getting more stable and more sure-footed. Tesla's latest public demos showed better pace and solid recovery when the robot slipped outdoors. Exactly the kind of oops moment factory robots must survive. That's the point. Trustworthy steps, predictable turns, and safe interactions around people and shelves. In contrast, Atlas is the athlete. If you've seen the clips, sprinting, vaulting, spinning, and flowing through parkour, you know it treats balance like a sport. Boston Dynamics' all-new electric Atlas has a wide range of motion, and the team uses those acrobatic routines as structured tests to push perception and control to the limit. G1 sits in the nimble middle. It's lighter and surprisingly agile for its size, with smooth body sway and eye-catching gymnastic moves like kip-ups and sweeping kicks that prove range and coordination. For speed, the leaderboard goes roughly Atlas first, G1 close behind, and Optimus in the same ballpark, but the real story is what for. Atlas trains for bursts of complex motion. Optimus trains for steady, safe work. G1 trains for flexible learning and demos. If you think walking and smooth moves make a robot the winner, think again. Hands are more complex, and they decide whether a robot can really live in our world. Optimus goes for human-like five-finger hands designed to hold everyday objects and tools, bottles, boxes, knobs, so it can learn the same tasks people do without redesigning the whole environment. Atlas favors robust, task-specific grippers for real industrial parts, and the latest platform adds new gripper variants with enough dexterity to grab, place, twist, or carry heavier, awkward items on factory floors. G1 is modular. Entry versions ship with simple fixed grippers or dummy hands, no dexterous fingers, to hit that low price, while EDU models can add dexterous three-finger or five-finger hands and tactile sensors so labs can study fine manipulation. If your goal is manipulate what humans use, Optimus's human-style hands are the obvious pick. If you're solving a defined industrial job, Atlas's grippers are honest and tough. If you're experimenting and tinkering, G1's menu of end effectors lets you choose your own path. Vision and brains are where these robots truly diverge. Tesla pushes a controversial vision-only approach for Optimus, leaning on multiple camera feeds and powerful end-to-end neural networks adapted from its full self-driving stack. No LiDAR, no radar, just cameras plus internal sensors for body feel. Because the bet is that scale, data, and training can make raw vision good enough, cheap enough, and general enough to work everywhere. Atlas and G1 go multimodal. Atlas uses stereo cameras, depth sensors, and body feedback to build a clear map of the world. It moves with a hybrid AI system that mixes classic planning with learned skills. Boston Dynamics and Toyota Research Institute now train large behavior models that control the whole body as one unit. G1 uses LiDAR and a depth camera, and it runs on an NVIDIA Jetson computer. Unitree is building one world model so developers can add new skills on top. Big picture. There are 3 paths to robot common sense. One bets on vision at large scale, one mixes rich sensors with classic control, and one stays open and modular so others can extend it. Power and charging shape how long a robot can work each day. Optimus has a big battery in its torso. It aims to run for a full work shift, which means fewer stops and easier factory schedules. Tesla's public specs and demos point this way, and engineers are still improving efficiency. Atlas switched from hydraulics to all-electric for a reason. It uses energy better and runs longer in real jobs, while still keeping its explosive agility. G1 chooses quick-swap convenience. Its compact, smart battery design favors faster turnarounds in labs. When power runs low, you swap the battery and keep going without waiting at a dock. Again, different settings, different answers. Let's put numbers on size and speed so you can picture them. Optimus stands about as tall as an average adult at roughly 1.7 meters and a lean build in the 126 pounds, 57 kilograms range, moving up to roughly 2.24 meters per second at top walking speed. A brisk, useful pace on a factory floor. Atlas is a bit shorter but far heavier, around 1.5 meters and roughly 196 pounds, 89 kilograms, with top speed clocked higher at about 2.5 meters per second as it trains those gymnastic maneuvers. G1 is the compact one at about 1.3 meters and approximately 77 pounds, 35 kilograms, portable, foldable, and easy to move between classrooms or benches, while still reaching walking speeds that keep up indoors. The silhouettes tell the story. Optimus looks like a coworker, Atlas like an athlete in armor, G1 like a sleek student intern. Payload and strength show the clearest differences. This is where these 3 robots split. Atlas focuses on firm, reliable grips and dynamic handling of awkward shapes. Car tires, brackets, heavy components during complex motion. Optimus is built to carry steady loads, picking and placing boxes, moving trays and parts, and bringing items on carts. Because that's where early factory wins live. G1 can lift lighter objects and gives developers a safe, capable body to prototype new behaviors before anyone chases heavy industrial use cases. If the job is to grab an uneven part and climb, step, or twist while placing it, Atlas is in its element. If the job is to carry a 44-pound, 20-kilogram bin to the next station every minute, Optimus is the right kind of strong. If the job is to teach a robot to sort delicate items or test a new manipulation policy, G1 is a friendly sandbox. Cost and availability are where the gap widens. Unitree's headline move was launching a humanoid at a price point that sounds impossible in this field, roughly the cost of a used car at the base level, so small teams, labs, and early-stage companies can actually buy and learn on a real biped. That alone changes who gets to participate. Atlas is not a retail product. It's a premium, partnership-first platform meant to crack the hardest jobs alongside a small set of customers. Optimus is not for sale yet. Tesla's target is less than a car, but that number only becomes real if the company hits scale and keeps the bill of materials in check. It's fair to say G1 is the easiest to buy today. Atlas is the most capable at acrobatics and rough and tumble motion. And Optimus is the most ambitious about becoming a common factory coworker at volume. How do they think through tasks? Optimus uses end-to-end neural networks trained from video. It learns like people. Watch, map, practice, repeat. Tesla is merging perception and control into one brain that sends joint commands. Boston Dynamics blends classic control with modern learning. Toyota Research Institute, TRI, trains large behavior models so Atlas can move, balance, and manipulate as one system. G1 stays open. You can use your own models, train on your own data, and push new skills to the robot. That is why it appears in so many research clips. In short, Optimus bets on big data and tight integration. Atlas bets on rich sensing plus hybrid AI. G1 bets on community and modular compute. Which one is best? It depends on the job. If you want a patient, steady teammate to carry parts, water plants, hand over tools, or repeat simple tasks near people, Optimus fits that future. Tesla is already training it on factory chores. If your space is messy, fast-moving, and physically tough, like construction areas, complex logistics cells, or lines with big, awkward parts, Atlas shows what's possible and is now aiming those skills at real work. If you need an affordable robot to test ideas, teach classes, or speed up research, G1 puts a humanoid within reach. Its sensor suite and SDKs are built for tinkering. This rivalry isn't just about who wins. It's 3 different bets teaching the field what works. Optimus looks like a careful worker from day one. It is built to learn home and factory tasks and to scale by the thousands. Atlas moves like a gymnast. Boston Dynamics uses agility as a research tool and then applies it to hard industrial motions. G1 is the easiest robot to put in a lab or startup without spending too much. That lets more people experiment. When you see a robot slip on a wet path and catch itself, jump a vault, or pop up from the floor, remember what you're seeing. It is 3 companies answering the same question with 3 different ideas: safety and scale, peak performance and open learning. The best robot depends on what you need it to do first. If you're excited about this, watch 3 signs over the next year. First, see if Optimus shows up in real numbers inside Tesla's factories and how long it runs between charges. Second, follow Atlas's first pilot jobs. Do those extreme moves turn into safer, faster tasks that save time and reduce risk? Third, watch the G1 developer community. When students and startups share a new killer skill that spreads from lab to lab, the platform is taking off. In the end, winners won't be chosen by one stunt. They will be the robots that show up every day and make hard, boring, or risky work easier. If you think that's crazy, wait until you hear this. What if I told you that right now, in a lab, people are building the first real human-like android? It uses fake muscles and a water pump heart. Not some clunky metal robot, but something that moves, feels, and acts exactly like you do. This isn't science fiction anymore. This is Clone, and what they're creating will blow your mind. The robotics world is having a massive moment right now, but most companies are stuck in the past. While Boston Dynamics is making robots dance, and Tesla's Optimus is learning to fold laundry, every single one of these robots uses traditional motors and rigid joints, fighting physics instead of embracing it. They're all trying to shoehorn human-like movement into mechanical systems that were never designed for it. The result? Robots that look human but move like machines. Clone's approach throws out the entire robotics playbook. While everyone else is obsessing over servo motors and gear ratios, Clone built something called a McKibben muscle system. Picture this: a rubber tube that grows bigger when fluid is pumped in. It is wrapped in a strong braided sleeve. When pressure builds, the sleeve squeezes the tube so it pulls tight in one line, just like a muscle. This simple trick copies nature. First, the muscles need water to expand and contract, just like real ones. That water has to be pushed with force. And here is the cool part. A pump in the chest works like a heart, driving the water through the muscles to make the robot move. Here's the crazy part about why synthetic muscles demolish traditional motors. Motors force engineers into constant trade-offs between speed, strength, and power consumption. You want your robot to lift something heavy? You sacrifice speed. Want it to move fast? Say goodbye to strength. But Clone's artificial muscles don't follow those limits. They copy the same system nature built over millions of years. Human skeletal muscle can contract with incredible force while maintaining speed and efficiency. Clone's synthetic version matches that displacement and pulling force, delivering human-level range of motion, strength, and speed simultaneously. They even started with the human hand, the most complicated part of our body, with its mind-boggling degrees of freedom and multi-articular design. They cracked it in just 18 months. We're talking about fingers strong enough to manipulate a knife through a dense pineapple, arms powerful enough to lift heavy cast-iron pans, yet precise enough for delicate manipulation tasks. The manufacturing advantage is equally insane. While companies like Tesla need expensive CNC machines and complex assembly lines to build motor systems, Clone's technology automatically produces muscle fiber by the miles. They literally just cut it to length and attach it to bones. It's like the difference between handcrafting a Swiss watch and printing fabric. The simplicity is revolutionary, and it means they can focus on the hard problem, making artificial muscles that perform like biological ones. But the real game changer is Clone's fluid system evolution. Early prototypes use compressed air. Air is easy to set up and quick for tests, but air is weak and not good for long use. The final android will use water instead, with a strong pump system. This hydraulic design makes the muscles work more like real ones. Think about that for a second. This robot will have a hydraulic heart pumping water through artificial muscles to create movement. Unlike your heart, which pumps blood to chemically activate muscle fibers, Clone's hydraulic heart pressurizes muscles directly for instant force transmission. The fluid literally turns into a rock when it hits the muscle for full contraction, creating what they call a very high blood pressure robot. If you are enjoying this breakdown and want more amazing robot updates, make sure to subscribe and hit the bell so you never miss out. When it comes to communication, forget everything you know about robot programming. You won't be typing code or using complicated interfaces. Clone envisions 3 phases of interaction that sound straight out of a science fiction movie. First, you'll teach the robot new skills by demonstrating tasks with your own hands. The robot watches, collects data with action labels, and learns from your movements. Eventually, a vision language action model will let you simply tell the robot what to do using natural language, based on massive data sets of language-labeled robot actions. The ultimate goal? Complete autonomy where the robot anticipates your needs and performs tasks without being asked. The brain powering this synthetic human is equally fascinating. NVIDIA Jetson chips sit in the robot's skull, controlling the entire system. If possible, they'll use 2. One for planning, one for motion control. But here's where it gets wild. Clone plans to distribute ASICs throughout the body, just like neurons in humans. Imagine processing power near the heart, at the wrists. Everywhere, fine control is needed for components like tactile sensing and the hydraulic pump. For sensors, Clone wants complete observability. Joint-level position and torque. Muscle-level position showing contraction length. Muscle force measuring pulling power. Tactile sensing for environmental interaction, plus vision and audio. Most of these are already implemented, though tactile skin got delayed because current robot control focuses on position rather than environmental force feedback. But they recognize that high-resolution tactile feedback will be crucial for future manipulation tasks that require delicate touch. So now I want to know what you're thinking. If you believe robots with water-powered muscles are the future, comment muscle. Alright, back to the video. Now here's something that might surprise you. Clone deliberately chose not to give their first android a human face. While the uncanny valley haunts every humanoid robot project, Clone's CEO explains that creating a compelling face requires absolute perfection. We're talking about 40 facial muscles replicating every micro-expression to avoid looking scary or unnatural. Instead of rushing this, they're treating facial features as a separate product line to be developed meticulously before market introduction. Smart move considering how creepy most robot faces look today. Up until now, many people have said the open muscles look a little scary. The next alpha version will fix this by adding skin to cover those exposed muscles, making the robot look more natural. More importantly, it'll feature the first version of a robot foundation model that enables learning new manipulation tasks from just a handful of user demonstrations. Imagine showing your android how to make coffee 3 times, and it masters the entire process. But here's the biggest technical challenge Clone faces right now: creating an untethered walking biped. The first synthetic human capable of independent mobile locomotion without external cables or pressure sources. This requires sophisticated physics simulation for locomotion training, plus incredible engineering to compact valves, batteries, hydraulic power units, accumulators, reservoirs, tubing, and cabling within the limited volume of the ribcage, abdomen, and pelvis. They're essentially trying to fit an entire hydraulic system into a human-sized torso while maintaining the robot's ability to walk, run, and perform complex tasks. This brings us to the bigger picture that'll blow your mind. Clone's CEO believes that while superintelligence doesn't technically require a body, giving it one makes it probably 1,000,000 times more useful to humans. Most tasks we want intelligent systems to perform happen in the real world, requiring physical interaction. But here's the kicker. Robotics will become a massive driver for modern deep learning and AI by providing high-quality, ground-truth data about reality. A scaled-up fleet of these androids collecting visual and tactile information could produce a form of superintelligence that's fundamentally different and potentially much smarter than anything we've seen. The Vision clone is chasing sounds like science fiction, but feels increasingly inevitable.